Thanks a lot. And I want to thank the organizers, first of all, for inviting me. It's my very first participation to Amplitudes, so as a participant, also as a speaker. So when I came here first, I was a bit I come from a standard model, collider background, so I was thought, okay, maybe I will be the different guy in the room. So I had to put some scattering amplitudes at high energy in my title, but also was one actually if QCD could make it in this conference. So following up on Anastasia's suggestions, I actually checked how many times QCD do appear in titles. Actually, so it's not too bad. So I think when you were complaining that people give a lot of to n equal 4, actually QCD is doing quite significantly better than equal 4. So I think they're still in business. And so I cannot really complain, as you will see, actually a lot of, clearly scattering amplitudes win the game. So, but then actually, so probably it's more interesting to look into slides if QCD is still winning, I guess, n equal 4, and it still is by very little amount. So with this, I can feel pretty safe being here because I come from a QCD background. I compute loops. So there will be some scattering amplitudes in my talk. So I'm pretty safe here. And actually, interesting looking into this, I checked that actually, interesting enough, there are still more problems than solutions. So I think we won't be jobless for the next few years. And on the negative side, there is very little love in the conference. And yet not enough negativity that will come in the afternoon, I think, with the other talk. So, and I think let's see if negativity overcomes love. So this actually brings me to by the way, maybe tomorrow with Lance we improve on n equal 4, maybe. So, but this is updated recently. So maybe this will win in the end. But okay, so Alex is really doing pretty well. And interestingly enough, Feynman, I thought that Damour would beat Feynman in this conference, but actually not yet. So Feynman is still somewhere here. But Damour, sorry? Yeah, well, so what? Yes, actually, yeah, you're right. But yeah, you're right. So fair point. So very good, very well spotted. Anyway. This can bring me actually to the serious part of the talk, where again, these are my keywords. So this is what we'll describe today. So with this, by reading left to right, you can basically understand my talk. So we'll be discussing some loop correction to scattering amplitudes in the Reg limit for QCD. There will be lots of gluons that regize, and I will try to describe this regization through the Balinsky-Jim-Walk evolution equation. And thanks to them, you will see that we can also able to derive some results in equal 4. So I also committing a sin here. And okay, I will not go through all of them, but just very briefly back to the title. This is work in collaboration with Fabrizio Caola and Giulio Gambuti in Oxford and Federica Devoto at Slack. So with this premise, I can safely go into my talk and start describing more. So it doesn't get more QCD than deep inelastic scattering, where here you have a high energy probe testing the partonic structure of the proton. Okay, well, very well known that this particular process can be described by just two variables. So the high energy transfer is Q squared and X. And X basically measures the partonic fraction of the struck parton, where Q squared again is the virtuality of the photon in this particular case. We've seen this plot already in the previous talk by Guoxing. So I still want to spend a couple of words on this because this will, it's helpful for me to both introduce some terminology, but also to motivate why we're doing these particular studies. Now, if you look at the partonic distribution functions, so these are just fits, so partonic distribution functions for basically C quarks, but also valence quarks. So in particular, if you focus on the gluon case, the red one, this is a very well-known rise of the gluon PDF at small values of X. So this X at fixed Q squared. So for two values of Q squared, this is a very well-known steep rise of the gluon PDF. And this is very well understood and described by the BFKL equation. So basically, you are fixing Q squared in this QCD evolution phase diagram. At fixed Q squared, you evolve in X. So X, small x is up here. And basically, this particular evolution is described by BFKL. Whereas at fixed values of X and large Q squared, this is the DGLAP that we heard just a few minutes ago, up to the point where you start hitting saturation regimes, where basically the non-linearity of the gluon interactions become very important. And this particular description, which is valid in dilute system, I will also come back to what a dilute system means later, needs to be complemented with a description in the dense regime, which is provided by the Balitsky and more generally Jim-Walk evolution equations for dense systems. But also there is a kind of a more amplitudes-driven motivation for this particular work that I'm going to present today, because basically it goes in the direction of studying QCD at high energy in the Regge limit. Regge limit, I will define it a bit more precisely later in the talk. And amplitudes show very important and striking feature in this particular limit. One of the most important one is the Reggeization of particles. I will be mostly considering the Reggeization of the spin 1 particle in QCD, which is the gluon. We've heard a lot about Regge trajectories just a few minutes ago. And what I will also be concerning with are basically how these particular amplitudes show universality features and how they organize in universal building blocks and give rise to basically a factorized pattern according to some suitable logarithmic counting. So this goes under the name of Regge-Pole factorization. And then you know that basically there's always a dichotomy. When you have a factorization property, you know that you can also draw some conclusion about resummation. So and this what I want you to take home from this particular discussion is that we can use amplitudes, in particular in this particular case QCD, but also n equal 4, to extract universal features of the theory, of the underlying theory, which is QCD. And then basically we can, and this will inform us really about QCD. So we use amplitudes as a tool to extract data and information about the fundamental theory, which is QCD. So this is pretty much the big message of my talk. So in more details now, let's move to scattering amplitudes in Regge kinematics. So the Regge kinematics for a 2-to-2 scattering is pretty simply defined as with the large invariant S. So S is the scattering of is the squared scattering energy of the two particles system. Is much larger than T, which is the momentum transferring along this channel. And we define X as the ratio of these two. This small x in this particular case means H much larger than T. And this, of course, at tree level is simply completely dominated by the T-channel exchange of a gluon. In this particular case, a 4-gluon amplitude, but if you have quarks, it's pretty much the same. This is dominated by the spin 1 particle of the theory, which Reggeize indeed. Reggeization means that this particular structure where the T dominance, so 1/T dominance is preserved by a loop, so it's not spoiled by loop corrections. And in particular, this complete factorization of the dependence in the amplitude from longitudinal variables like S and transverse variables like T. So the only corrections in S will come through logs of basically coming from the gluon Regge trajectory. And by the way, I want to stress here that for me, the Regge trajectory in this particular talk will be the exponent of the dress gluon. So basically, I will be talking about a lot about regions, which are the effective degrees of freedom that describe the theory in this particular limit. Now, moving to the multi-Regge kinematics case, where you just don't have two emitted particles in the finite state, but you have a ladder of strongly ordered particle in rapidity, where you have up to n. And basically, this particular scattering is better formulated by saying that all these finite particles are very strongly ordered in rapidity, as we just said. And if you translate the rapidity in terms of invariance of pairs of particles, you see that basically at fixed transverse momentum, there's no hierarchy in the transverse momentum of the standard particles. Rapidity, growth in rapidity means a growth in invariance. So basically, if the energy increases, so basically, this limit can also be described by the fact that each pair of particles have increasing invariant mass at fixed values of the transverse momentum of each individual particle. So now this at leading logarithmic accuracy, the logarithm that I'm just referring to is the log that comes from expanding perturbation theory, this particular Regge trajectory. This can be organized as a ladder diagrams where you have Regge trajectory. So these are exchange of effective regions interacting with the standard gluons through an effective universal vertex, which goes under the name of the Lipatov vertex. And this will also be quite part of the, I will dedicate quite some attention to this particular object here. Again, so these are all universal objects, and the amplitude factorized in this particular very nice way. So I have to spend a couple of words on color and signature amplitudes, because this is how amplitudes are eventually finally organized in this particular limit. So if you take, basically you have two light cones here. By light cone, I mean two very fast moving particles, two projectile. There is some background where basically they interact through, you can also think of one particle like 1,5 moving through the background generated by this line, and then there is an external gluon here. And basically, signature symmetry means that we are considering basically a permutation of the direction of this particular light cone. And amplitudes are neatly organized in this particular, if you take into account the signature of the channel exchanges, so the first channel exchange and the second channel exchange in this particular 2 to 3 case, then amplitudes can be organized in minus minus, which is you have a minus symmetry in this particular combination here, where you see I'm swapping particles, and even odd, odd even, and even even. Okay, this should be even even. Sorry, not even, a typo there. And also this speaks with color, of course, because you basically what we want to do here is to describe the T channels as an irreducible representation of SUN in this particular case. For example, in the case of gluons, so if you have 2 gluons along this line, you can decompose the T channel here in this particular way. This is a well-known decomposition in irreducible representation, and the same for quarks. So basically, the signature of the amplitude and the color of the amplitude tells us basically what kind of quantum numbers are being exchanged in this particular T channel. And we know that the gluon is basically lives in the adjoint antisymmetric representation. So this means that basically the region carries indeed the same quantum numbers of the gluons. So now, if we move to next to leading logarithmic accuracy, so basically we start considering quantum correction to basically QCD quantum correction to all the contribution that describe this particular ladder. So there will be impact factors, and these are the only flavor-dependent objects in this particular picture. There are quark and gluon impact factors, but the rest, anything which is central to this particular picture, reg directory, and the central emission vertex are universal. So basically, this factorization can also be stated by saying that amplitudes in the Regge limit, once you account for impact factors that can be flavor-dependent, they are universal. So that's basically a statement of universality of amplitudes in the energy limit. This is what I will be after. Now, this is true for the minus-minus symmetry that I just described before, where you have an octet exchange in both T channels. But actually, beyond what is usually referred to the Regge pole, so beyond the pole, there will be Regge cuts, where you have basically. Is it off? Okay, now better. Sorry. There will also be contribution to these particular amplitudes, and I will come back to this at some point later in the talk. But for now, I want to stress the fact that this can be universal in this particular configuration. Now, very quickly, just a few words on why we're actually interested in going beyond next to leading logarithmic accuracy. So basically, if you remember the very first slide, not the very first, but at some point I described that we want to describe, for example, the rise of the gluon Partoian distribution function at small values of x. This is completely predicted by BFKL, but also the description of this regime can be improved by BFKL evolution equation. And the way this is improved is by basically, if you write down the evolution equation, the BFKL evolution equation for what is so-called the gluon green function, which is what sits in the middle of these particular graphs, then basically the logarithmic accuracy is controlled and improved by improving the perturbative accuracy of the kernel. And then basically where we are now, and this is a result, I think, of 24 years ago, I believe. So that's where we stand. And after 24 years, we have not been yet done computing and understanding the whole next to next leading order part of this BFKL evolution equation. There has been a lot of progress. Here, I just want to mention that the genuine next to next leading log contribution, which are basically a 3-loop Regge trajectory, has been computed, and this is what I'm going to discuss today: the 2-loop correction to the central emission vertex. And there is some work going on, for example, for better understanding the multi-emission case in the next to multi-Regge kinematics also, and there is Juju here. Recently, some work came out this week, so I invite you to look at that. Now, back to amplitudes. So how do we actually go about studying these universal effects of QCD amplitudes? So basically the idea is that as soon as you go, this is a well-known problem, that as soon as you go beyond next to leading logarithmic accuracy, this simple picture of a single region exchanged in the T channel actually is broken. So one cannot find universality of scattering amplitudes in this particular regime. Factorization doesn't hold anymore. And this is due to the fact that you start having multi-region exchanges in this particular case that respect this minus-minus symmetry, but also respect color. So basically this starts for the first time at 2-loop. And this is basically what spoils this particular universality of the amplitudes. And I want to stress here that non-universality for me means that they depend on the species of particle you're scattering. So these contributions are different if you scatter gluons or quarks. And then what's actually very interesting to observe is that this is a purely finite NC effect. So a leading NC, so in the planar theory, you wouldn't see this kind of effect. So this is a purely QCD finite NC effect. Of course, in N=4, there are also there in the non-planar case. So our goal here is to recover universality of scattering amplitudes. And we do this by basically expanding some results for 5-point two-loop QCD amplitudes that we computed some time ago in full kinematics, expanded to multi-region kinematics. And then we want to recover this particular non-universal contribution by exploiting rapidity evolution equation in the form of the Balinsky-Jim-Walk evolution that I mentioned in the beginning. And then finally, we want to match this in quotes EFT approach to the full theory and extract universal coefficients, which would be then the main result of this discussion. So basically, how this I'll just spend very few words on this. So we start with the full kinematics two-loop QCD scattering amplitudes in the 5-point kinematics. So we heard, I think it was on Monday or Tuesday, Monasteries, I don't remember, how the symbol looks like in the full kinematics case for 5-point. In MRK, it simplifies dramatically, of course. It goes down from 31 letters to 12, and which are completely separated in longitudinal variables from the transverse variables that describe the dynamics in the transverse plane here. So actually, as far as the mass integers are concerned, here the picture is much more simplified than the full kinematics case, and one can derive the results in written down in terms of logs and polylogs, as I will say in a second. But also there is kind of an interesting, for example, observation about how part of these letters correspond to completely unphysical and spurious singularities and their fate of their cancellation depends on what kind of objects you look like. If you look at like a UV normalized amplitude, a finite remainder, and then eventually, for example, some of these singularities actually survive and they only cancel out when you expand close to these particular limits, just because they are accompanied by rational factors, meaning that, for example, in N=4, actually there are not as many as in this particular case in QCD. So now just spend again just a couple of words on how these amplitudes in MRK look like. So basically, one interesting thing to observe is that there was already a work on N=4 by Simon and Johannes a few years back. And then what we, for example, control is that what we checked is that the principle of maximal transcendentality here is also confirmed. So basically, we can, if you take the limit where the GG scattering is, we only consider the maximal transcendentality part of the QCD gluon-gluon scattering amplitude, we recover the N=4 result, which is well known not to be true at the full amplitude level, but in this particular case, it holds. One could have expected this because we know that the BF-KL kernel in general, it respects this principle. Although here we're comparing only a piece of that. So I think it was also still kind of an interesting observation, maybe not super surprising. But also here I just want to flash the one loop, this is a complete one loop odd amplitude, which fits in one line, which for me it's kind of a miracle that I can write down an amplitude even at one loop for a QCD amplitude. And you can see that here you observe the N=4 result, and here some basically these just go away when the number of when the representation of the quarks is equal to the ones the quarks are in the adjoint, and then finally these are basically rational contributions. And then there are some interesting observations also that one can make about the amplitude, and just one that I want to mention is that at leading transcendentality, so at weight 4, there is no genuine polylogarithmic of weight 4. Actually, only the highest thing we get are powers of logs or logs to the 4. And the first genuine highest weight function is a Lie 3. So it's also kind of an interesting observation. So now moving to the rapidity evolution and how we use this to match to the theory and extract interesting information. So here, again, this goes, basically we use the Balinsky-Jim-Walk rapidity evolution that we just mentioned in the beginning. This was devised, again, to describe basically dense media, where for example, heavy ions or nuclei at very large energy next to the saturation regime. It can be written in this particular form. So basically, it's a rapidity evolution of products of infinite Wilson lines through an Hamiltonian, which is the Balinsky-Jim-Walk Hamiltonian. And in this particular case, we write it down as a sum over dipoles. And then basically, you see that you have two terms, one which describes the interaction through a gluon of two infinite Wilson line that do not cross the background. This is basically, the idea is that to describe the motion of infinite Wilson line in a QCD background. And then there are also cases where the gluon is exchanged and interacts through, it goes through the background, interacts with the background, and then reabsorbed back from the other Wilson line. Now, the problem with this equation is written in this way. This is an unbounded system of equation for Wilson lines, so there is no hope to solve it in closed form. And I mean, nobody's really solving this in closed form. There are special limits, for example, the planar case where this can be written down in closed form. It was also work by Müller. But actually, the key observation and the very clever, of course, observation by Simon Carreau, basically 12 years ago, is that after all, we're working with quark and gluons at high energy. So we're in this dilute system of basically single individual partons. We're not working with dense in a dense medium. And also, we're basically, since we are at high energy, we can work in the perturbative regime. So we're basically in this sweet spot where we can work in the dilute regime, where we expand. So the idea is to expand these Wilson lines close to unity, and basically introducing an auxiliary field, which I will call W. It's called in the literature, it's called W. This can be sometimes referred to also, sometimes also called the region. I wouldn't go that far myself yet, because I think next to leading log, this equivalence is not really on solid footing. But if the word region slips out of my mouth, please forgive me. But okay, this is basically W field close to a region field. And then this particular evolution equation is completely linearized, and one can hope to solve it, perturbatively, and basically try to understand the rapid evolution of products of Wilson lines in this perturbative regime. So now, how does this work? So again, we take an infinite Wilson line, we expand it close to unity in a perturbative way, and then basically the idea is that, of course, this works when there is again a background. So basically, we're expanding an infinite Wilson lines in the background of another particle. In our case, could be the second light cone, and then we have at a given order in perturbation theory, a fixed number of exchanges of these W fields. So the idea is that, for example, if you now study this evolution equation for a single W field up to 2 loop, this gives exactly the rapid evolution of the region. So that's why, at least next to leading log, one can safely make the connection between this W field and the region, just because the eigenvalue of the rapid evolution is exactly the 1 loop gluon region trajectory. Now, the Hamiltonian here that we just saw before allows for transition between multi-W states, but actually the W is a signature preserving field. And basically the idea is that there cannot be transition between, so they only allow transition between n and n+2 fields. Now, in our particular case, since we want to extract information about the odd amplitude, where we hope to see Rege-Pohl factorization, the only thing that we're interested in is a very technical point, is basically just the leading order Balinsky-Jim-Walk Hamiltonian. And basically what allows us to write down is basically any product of these, any correlators of these 2 W fields can be written basically using the Wick theorem. And we just have to specify what is the same rapidity correlator for 2 W fields. This was a technical point, but I just want to make it clear that these are the assumptions that we work in. And then now, basically, the extra ingredient that we need in our particular calculation that went a little bit beyond what was in the literature is that we need to describe the interaction with the central emitted gluon. So basically, we expand these Wilson lines close to unity, and then at some point we have to evolve these Wilson lines, these W fields down to the rapidity of the central gluon, and we need to basically write down an operator product expansion for the external gluon field, which is an actual gluon, and the W field. So okay, this basically what it will take is that we need to describe basically the interaction of one reg and one W field, or 2 W fields or 3 W fields with an external gluon. Now, in the particular case of one, for instance, just to show you, to convince you that there's not just a lot of nice pictures, but also some formula. So basically, if you expand perturbatively the interaction of a single W field with a gluon, you get basically a series of evolution that go from 1 to 2 and to 3. And this can be written down in a very simple form. And this can basically be computed using usual standard Feynman integrals techniques. Now, this is just a very quick recap of what I just said, because I know that sometimes it can be a bit complicated to digest. So basically, we start with a Wilson line. We expand it in the dilute field regime. And then basically in perturbation theory, we have a fixed number of these W fields. We evolve them down to the central rapidity using the Balinsky-Jim-Walk evolution linearized now, We evolve them down to the central rapidity of the gluon. We use an OP expansion to describe the interaction of these W fields with external gluon. And then yet we expand, we do the final step in the rapidity evolution, and we go down to basically we have the products of W fields at the same rapidity, and we can use Wick theorem to work there. So now we want to match these to the scattering amplitudes that we computed in order to extract universal objects. So here I just want to quickly flash an interesting feature of this particular effective theory description, that basically it predicts exactly and fully, I want to stress it again, exactly and fully anything which is not in the odd amplitude. So basically we can get the full amplitude for anything which features double region exchanges in either of the two light cones. So, and this will be completely predicted by the theory. Of course, what is not predicted is the leading order or leading log contribution, where basically we need to have we need to match, like in the usual EFT framework, we need to match to the fundamental theory the coefficients of the expansion. I just wanted to flash a couple of how the results for example, for a 3W evolution down to 1 or 3 to 3, they look like. They can be written down neatly as a combination of Corel operators. And this contributes eventually also to the odd amplitude, where we want to extract our final results. Now, basically, this is the expansion of the next to next leading log amplitude, the 2-loop, where we have basically this is the object we want to extract, the 2-loop correction to the central emission vertex, because all of these other particular universal building blocks in this factorized form are known from previous calculations. And this is what basically generates non-universal contribution that we can completely predict as we just described. And I want to stress is this at this particular order are theory independent. So basically we have them for n equals 4 QCD, but basically any theory which features the exchange of gluons. And now there is so basically there is a slight ambiguity in the calculation of this object, because I just told you before that this non-universal contribution comes from finite NC contribution, whereas the theory, so the effective theory predicts also leading Corel contribution of these particular exchanges. So now we need to find a scheme where we decide if this leading Corel contribution predicted by the theory go into the universal part, because they are universal, or so basically if they belong to the Regio pole factorization and the BFKL evolution of the amplitude. So we adopt a particular scheme where all these NC squared contribution, which are leading Corel and universal, are absorbed into the definition of the vertex. So, okay, this I can safely skip. I just want to say that basically with this last calculation, we now have pretty much all the objects that we need to describe basically 2-loop amplitudes for arbitrary number of external legs in the multi-reg kinematic limit. I just want to flash very quickly our result for the 2-loop central emission vertex in QCD n equals 4. Where again, this was extracted by exploiting the maximum transcendentality principle. And you see that this it's super neat, just fits in less than half a line for one loop, and the 2-loop is actually very simply written down here. And you can see, you can appreciate that it's really written down in terms of simple logs. So there is nothing more complicated than a log in this particular result. Logs of these transverse variables and also this is the QCD result. Of course, it looks a bit more complicated, but you can appreciate the leading Corel contribution. This contribution that would just go away again if we go in n equals 4. And then basically anything which not, I think I'm done. Yes, very good, thanks. I'm there. And basically just want to highlight the fact that here, of course, that there is a dependence. I mean, there is so not just transcendental function, of course, in QCD, but also rational functions. I want to stress that these rational functions are extremely simple, even in QCD. There are 6 of them. They respect very particular symmetry of basically exchanging the two light cones. And so basically imposing this symmetry of exchanging the two light cones and imposing basically and knowing the set of functions, actually this result is highly constrained. It looks complicated, but this is really highly constrained. So maybe it will also be interesting to study in the concept of bootstrap. I'm not an expert, but I think already we managed to constrain some of the structures even without calculating the full result. Here I just wanted this brings it to my conclusion. I just want to make again the point that it's in the interest that we had in studying QCD amplitudes in the high energy regime comes from the fact that we can learn something about the fundamental theory, meaning that we can extract universal objects. And again, this will improve substantially, for example, the description of amplitudes in a factorized regime, but also allows for the resummation program in the BFKL in the BFKL fashion to be advanced to next leading log. This was something that has been waiting for 25 years from the PDF and QCD community. There is also kind of a discussion if it is really important for Higgs physics related studies, given the recent discrepancy has been seen by improving the description of the Poisson distribution functions in calculating Higgs boson cross-section, which is an extremely important observable at the LHC. But also studying in general high energy dynamics basically will also bring a lot of interesting conceptual issues that come at the second order, especially when finite and C contributions are included. And also want to urge you to listen to Ira's talk this afternoon about how this looks in gravity, what kind of different features are there, what kind of features are similar. And maybe this is also an invitation for part of the audience here that is working on 6-point two-loop QCD amplitudes. So we heard a talk a few days ago. There is a kind of some interest that maybe one could already see the universality of amplitudes even in the 6-point case, but basically assembling these building blocks that have been provided here. So it will also be another interesting observation of Regge-Pohl factorization, universality of scattering amplitudes in a more complicated case like the 2 to 4 case. With this, I conclude, and thank you for your attention.